Hello everyone. Today we are going to analyze this cantilever beam. In this beam, we have uniformly distributed load W per unit length. It is acting for the whole length. Now let us apply this rule and find the vertical reaction RA. RA is acting upwards, so it will be positive. The UDL is acting downwards, so it will be negative. We have to multiply the UDL with the length L, so the total load will be WL. For RA, we will get WL. To find MA from the point B, let us take a moment about A. In this case, we have to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. The UDL is acting in the clockwise direction, so it will be negative. The shape of the UDL is rectangle. We have to multiply the area with the centroid distance. The area is W into L. The centroid distance from the center to the point A is L by 2. So when we find the moment for the UDL, we have to multiply the load with the distance and then the distance by 2. MA will be acting in the anticlockwise direction, so it will be positive. For MA, we will get WL square upon 2. Now I am going to find the shear force values from the point A and towards the point B. In this case, we have to follow right hand side rule. Upwards will be positive and downwards will be negative. The shear force at just left of A is 0. The shear force at just right of A will be WL. It is acting upwards, so it will be positive. Let us find the shear force at B. It is acting upwards, so it will be positive. The UDL is acting downwards, so it will be negative. For the UDL, to get the total load, we have to multiply the load with the distance, so it will be WL. For the shear force at B, we will get 0. This is the shear force diagram. Now using the right hand side rule, we can find the moments. Let us find the moment at A. In the point A, we have MA which is acting in the anticlockwise direction, so it will be negative. We know that the moment in the free end B will be 0. Here you can see the bending moment diagram. The shape of the diagram will be second degree parabola. Using this diagram, we can find the slope and deflection in the point B. The formula to find the slope is area upon EI. This is a second degree parabola. The area formula is 1 upon 3 BH. Here the breadth is L and the height is WL square upon 2. So this is the area. The area divided by EI, we will get the slope, which is WL cube upon 6 EI. Now we are going to find the deflection at B. The formula is area x bar upon EI. The area we know. The horizontal distance of center of gravity from the point B is 3 upon 4 into breadth. Here the breadth is L. So it is 3 upon 4 into L. We have to multiply that. For the deflection at B, we will get WL power 4 upon 8 EI. Alternatively, we can find the slope and deflection at any point of the beam using double integration or a Macaulay's method. We need to make a section in this beam. You can see that I have made a section at a distance of x from A. We have to find the moment at the section. I am going to find from the point A. In this case, we have to follow right hand side rule. Clockwise will be positive and anticlockwise will be negative. MA is acting in the anticlockwise direction, so it will be negative. The reaction WL is acting in the clockwise direction, so it will be positive and the distance is x. The UDL W is acting in the anticlockwise direction, so it will be negative and the distance is x. We know that with the UDL we have to multiply the distance and then the distance by 2. X into x, it will be x square. We have to equate the movement with the EI d square y upon dx square. We have to integrate on both of the sides. When we integrate this, we will get dy upon dx. We can integrate these three terms using this formula. In this term, there is no x, so the integration will be x. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. C1 is the constant. 2 into 3, it will be 6. One more time, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. When we integrate x cube, it will be x power 4 upon 4. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. 2 into 3, it will be 6. 6 into 4, it will be 24. In the point A, there is a fixed support. In the fixed support, there will be no slope. dy upon dx is the slope. We know that from the section we have made. In the point A, x will be 0. In this equation, for x and dy upon dx, we can apply 0. In this way, we will get z1, which is 0. Also, in the fixed support, the deflection will be 0. Y is the deflection. In this equation, for x and y, we can apply 0. In this way, we will get C2. In the slope and deflection equations, we can apply the values of C1 and C2 so that we will get these two equations. First, let us take the slope equation. We can take EI on the other side, so it will come in the denominator. We can take W outside. For these three terms, we can take LCM. Let us keep 6 as LCM. We will get this equation. Using this equation, we can find the slope at any point of the beam. Let us keep this equation as number 1. Now we need to find the slope at B. In the point B, x will be L. So in this equation, instead of x, we have to apply L. In this way, for the slope at B, we will get minus WL cube upon 6 EI. Now let us take the deflection equation. We can take W outside and EI on the other side. It will come in the denominator. For these three terms, we can take LCM. Let us keep 24 as LCM. This is the equation of deflection. Using this equation, we can find the deflection at any point of the beam. Let us keep this equation as number 2. To find the deflection at B, instead of x, we have to apply L, so that we will get the deflection at B, which is minus WL power 4 upon 8 EI. It is the elastic curve for the deflection. Here you can see the summary of what we have done. Using these two expressions, we can make one more expression. Let us assume that the uniformly distributed load is acting only for a distance of A from the fixed end. To find the deflection and slope at C, in those two expressions, instead of L, we have to apply A. From C to B, there is no load, so the elastic curve will be straight. In this case, from the point C to the point B, the slope will be same. Let us take this triangle. In this triangle, we can use the tan theta formula. Tan theta C will be equal to the opposite side. Let us assume that the opposite side is y upon the adjacent side. It is L minus A. The value of tan theta C will be very small. In this case, we can approximately take tan theta C is equal to theta C. So theta C will be y upon L minus A. We know theta C. We can apply that. We can take L minus A on the other side. It will come in the numerator. To find this height, we have to add this and we have to add this. This height is the deflection at C minus W a power 4 upon 8 EI. This height is Y just before we have found. We need to add both of them. From these two, we can take minus WA cube upon 2EI outside. For these two terms, we can take LCM. We can keep 12 as the LCM. Finally, for the deflection at B, we will get this expression. Suppose the uniformly distributed load is acting from the distance of A to the free end. We can easily make the expression for the deflection at B. From this, we have to subtract this. Here we have the negative sign. So negative into negative, we will get a positive. We can take W upon 8 EI outside. We can take LCM. We have to multiply this with 3. 8 into 3, it will be 24. Finally, we will get this expression. Now we are going to end this session. Thank you for watching this video.